Thank you. So first of all, I'm delighted to be here. And I was lucky to meet Maxim long ago. So we met the very first Monday of September of 1980, when Maxim just became 16, like a week ago, or maybe like 10 days ago. And he, at the age 15, he entered Moscow State University. At the age 16, turned 16, he came there as a freshman. He came to Gelfand Seminar. So that's where we met. Actually, I heard about Maxim as about this great high school kid 2 years before that, but didn't see him. And so we were talking ever since we get to the same point of space-time. And it was a kind of incredible joy of my mathematical life to be able to talk to Maxim and to be able to discuss what happens in mathematics, what is mathematics, and how to do mathematics with him and what's going on. And I should say that there's many things you all know Maxim. So, but among other things, so it was great that Maxim always thinks about things in a very simple way and very non-technical way. And so when you have a chance to talk to him, so you get the picture in the best possible way, and he explains this picture using the minimal number of words, and sometimes even less than that. And on the other hand, I mean, it's his universality. So again, we all know that. Excuse me, this frivolity. I kind of imagine when I was flying here that Maxim met three great mathematicians, Euler, Thurston, and Grothendieck, in the kind of beginning of his career. And he would come to them and say, I have some simple story to tell you. So he would tell the story. And each of these mathematicians would think that, yeah, this is a guy who picked up my style. This is my style mathematician. But then notice that these three mathematicians probably would never talk to each other. So that's kind of universality of Maxim. And this universality was present essentially from the very beginning. I cannot say like 34 years ago, because he did not maybe too much mathematics years, but definitely in a few years. So his approach to mathematics was kind of universal. There was no divisions on branches of mathematics, no geometry, no algebra. So it was all together, and attempt to understand the simplest things, simplest terms. And at that time, some citation from Maxim, I remember if somebody approached him, me for example, asked some kind of question which wasn't quite kind of too special, Maxim said, I'm a specialist in general questions of mathematics. And so, you remember that? This somehow disappeared later on, as far as I understand. I mean, you no longer say this. But so this universality and simplicity was from the very beginning. So somehow it was kind of internally in him from the very beginning. And again, so I'm very happy that I had a chance to somehow to see how Maxim grows and talk to him. And so I can only hope that for the next 34 years I would be able to understand what you're talking about. Okay, sorry, let me start now the talk. So I'm talking about Hodge quantum field theory. So I'll start with analogy. So let's suppose that we have M, which is topological threefold. Then let's suppose that we have two loops here, A and B, which are homologically trivial. I'm writing. The class of A is and the class of B equals 0 in H1 of M. So homological trivial. Then we can talk about linking number. We can think about the linking number. Let's denote this like AB. So this is some integer. And A and B. And so this
The 1, 1, H2.
Huh?
You didn't say H1 and T were the main problem. Depends.
I mean, let's suppose just homological sphere or just
Yeah, you didn't say the same. Otherwise, not true.
yeah. So, and then that's, I was going to say this next word. So this is actually the simplest correlator in Chern-Simons, like Maxim was considering this 20 years ago. This is the simplest correlator in a TQFT. And then you can talk about Chern-Simons, as Maxim did, and develop the whole theory. So this is topology. Now let's look at, I would say, analysis or arithmetic. You have a Riemann surface. Then let's assume that you have two divisors here. And let's assume that their degrees are 0. And so the picture is like that. You have B, you have A. And then there is a notion of a green function, g of xy. Let me remind you what is a green function. It's just a solution of the differential equation dd bar of g of xy equals delta function of the diagonal. So diagonal. Yes, it's a real valid function which solves this differential equation.
Let's say, because that's why there's like a thing which makes life difficult if you don't say domains, etc.
So it's a green function. I try to use a less number of words, but not so. So it's a green function. You're right, Misha, you're right. It's a real valid green function. Actually, it's a current which generally solves this equation. So here is a harmonic representative of the class of the diagonal. Otherwise, it doesn't have solution. And it was a great idea of Parshin and Arakelov. So it was suggested by Parshin to Arakelov to say that if you consider this green function evaluated in these two divisors, then it's independent on the, it slightly depends on the some choices here, like choice of hermetic. Then this is completely well-defined function, real valid function. And the Arakelov said that this should be considered as an intersection number. At infinity. I don't want to elaborate further to that because then you have to talk about algebraic curves defined over rational numbers and about height pairing, and then this will enter as a key. It's a number, yes, this is a number. It's a real number.
It's a function.
Yeah. Maybe I should say this is like g of A0, B0 minus g of A0, B1, and so on. It's a number. Huh? What's the problem with that?
The green function has particular, so zeros and poles here and there, right?
No. You take green function. It's a function of two variables, x and y. So for every pair of points on the curve, you have a number. Okay. Now let's suppose that you have 2 points which you count with signs plus and minus. And then you extend this function by linearity. So you get formula like that. It's still a number. And so Arakelov suggested that this number is a kind of intersection, it's a part of height pairing, but it's kind of intersection index of these two divisors in a sense which is a little mysterious, and the whole Arakelov series, coming from here. Now let's do this analogy a little better, just a little better. So we want to say that this g of AB is actually a linking number. It's a Hodge linking number. Again, it's not clear what it means, just words. And so, but still the picture, the mental picture which we have about this is the following, that we imagine that we have some space X, which is like, it's 3D. Now it's 3D. It still come from our surface in a certain way. And then the space is fibered, and the fibers are actual Riemann surfaces over some space which is one-dimensional, 1D. And so this is a classifying space of some group, algebraic group I'm going to talk about, Hodge-Galois group. And so it's not clear yet what this is, but the point is that whatever it is, it's like a bouquet of circles. And in particular, there is one map of this single circle to here. And so now talking about linking numbers, any point x in the original curve gives rise to a section let's call S sub x of this imaginary fibration. So again, we don't quite say what the section is, but then we kind of postulate that if you take sections, these sections evaluated as A and as B, then their linking number in this 3D manifold supposed to be is defined as a green function which has been defined before. So it's just an analogy, but it explains what I'm going to do. So what I'm going to do, I'm going to take as a motivation the story which is going on for odd dimensional manifolds, and I'm going to develop something like that, but different, quite different, which is going for complex algebraic manifolds, where the green function will be the simplest possible thing which I get out of this. So the goal, want to define this quantum Hodge field theory such the way that first of all it should provide another language for usual Hodge theory, and secondly it is kind of Hodge version. It can be viewed as a Hodge version of Chern-Simons on odd-dimensional manifolds. All right, so before, and again, the last thing, so it's not going to be some discussions about this. We will be talking about some concrete things which come in of this. And so we define correlators. Now, before I go to that, I still want to make this analogy more precise, a little more precise. And so I need to explain what the Hodge-Galois group is. And so I need to say what the Hodge theory tells us. So the next topic is, what is the Hodge-Galois group? Yes?
Is there any relation between this linking number and the way you define it as a correlator on the Riemann surface and something like WZW models, which would be holomorphic on Riemann functions?
I didn't, Sergey, let me try not to go into this, because I didn't even define anything yet. So
let me give this lecture first.
Yeah, so otherwise I will run out of time very quickly. So let me start from some definitions which many people know, that a weight and pure Hodge, real Hodge structure is a very simple data. It's a vector space V over real numbers, and filtration on the complexification of this vector space VC, such that this vector space we see after that is presented as a sum of its components Fp of Vc intersect Fq of Vc bar, where P plus Q equals to N. This is a weight N Hodge structure. And they form category, and the category of pure Hodge structures is equivalent to the category of representations of group. I mean, algebraic geometers will kill me unless I write this thing. What it really means, this algebraic group whose complex points are just C star cross C star, and it's over reals, so the complex conjugation acts by interchanging the two. So it's basically a representation of C star cross C star with some reality conditions. That's why you get this P and Q numbers. And then this is just a pure Hodge structure. That's what we find in the cohomology of algebraic varieties which are compact and smooth. And then there was Deligne who said that there is a thing which is more general, works for any varieties. It's a mixed real Hodge structure. And so according to him, this is just a vector space V over R. And it has two filtrations. The one filtration on the same vector space, which going up, it's called the weight filtration. And another filtration is going down, and it is on the complexification of this vector space. So this is a Hodge filtration. So it's linear algebra data. And the condition was that if you consider Wn of this V R, this is pure R Hodge structure of weight equal to n, for any n. And then it was a very surprising theorem, if you think about this, that these guys form an abelian category, proved by Deligne. And then using this fact together with observation that there's a fiber functor. So let's call this category of real mixed Hodge structures. And again, Deligne proves this is an abelian category. This is not at all obvious, and I mean, hard to believe. I mean, I don't know how Deligne get to this idea. So, I mean, from some argument, from some ideology of motives and so on. But I mean, it's not that easy to see this right away. So there is an obvious functor, just to the vector spaces over real numbers, which assign to this Hodge structure the original vector space. Now we are in business because, as Tanaka and Grothendieck teach us, we can take the aftermorphisms of this tensor functor, and these aftermorphisms form a group, a pro-algebraic group, which is called G Hodge. So this is the definition of the Hodge group. And there is a structural theorem which says that this group looks as follows: that this group G Hodge projects down to the group GMC over R, the one which was introduced there, and the kernel of this map is a pro-unipotent group U Hodge. And how we see that this is true, there is a functor, if you just consider the associate graded for the weight filtration from real mixed Hodge structures. By definition of what mixed Hodge structure is, you go into pure Hodge structures over R. And then, of course, there is a functor back. And this means that there are two maps between the corresponding groups, between the Galois group of this category and Galois group of that category. And this means that not only we go this way, but there is a section here. So, OK. Now one can summarize this whole discussion by saying the following: that this second functor, taking associate graded for the weight filtration, is equivalence between the category of R mixed Hodge structures and the category of Lie-U or just U Hodge models in the category of pure Hodge structures. It's a little, maybe a little looks like a little complicated way to say that the original category is category representation of G Hodge. But you can phrase it in this way using the semi-direct structure of G Hodge. This is just representations, category representations of the unipotent part, but in slightly different, richer categories and vector spaces. All right, why we need this? Let's go back to our linking numbers. So now I can say more precisely what all this analogy is supposed to mean. This one. So if you just take first dimensional homology of this curve x minus a modulo b with real coefficients, then this is, as Deligne tells us, it's a real mixed Hodge structure. And therefore, it has to be understood as a representation of this Hodge group. And so first of all, we have to take associate graded for the weight filtration. And it has three pieces. Two of them are very easy, just one-dimensional vector spaces in degree, I mean, of weight 0 and -1, -1. And in the middle stays the homology of the compact curve. And then, so just this guy is element in this category, in the category of pure Hodge structures by definition. Now, if you want to have a mixed Hodge structure, we need to act by some unipotent Lie algebra here, which makes weights go down. And the only non-trivial operator which we're going to see is this operator GAB. So the little theorem is that this green function, which I thought about as an intersection number, or Arkelov as intersection number, or as a linking number, there's nothing else but precise description of this mixed Hodge structure by a single operator. Oh, and then one can explain, I mean, more analogous what it has to do with linking number, take an exercise. I'm not going to talk about this. So assume that you have a family of circles over an actual circle, and then exercise define linking numbers the same way. So you can do this. as this kind of monodromy. So what this operator means, I want to emphasize this again, that over this, oh, here it's good. Over this imaginary, I mean, not quite imaginary, now we define this group, so there's this classifying space, which topologically bouquet of circles, and there is a single circle here. And so what we're doing, we kind of taking monodromy around the circle, and we get to this green functions. That's what it means. That's another way to interpret this. OK, now, after this kind of easy analogies, let me go to a little more sophisticated analogies, which grow from here. And so again, we run analogy between arithmetic and geometry, or analysis. So then the next step, we have Galois world, and we have a Hodge world. And let's suppose that we have some field K, and let me even assume it's embedded to C. Then here we have some algebraic variety over K, and here we have some algebraic variety over C. And here we have the Galois group, the absolute Galois group. Now here, we already know that we have an analog of that. So what is this analog? So the point is that the Galois group acts on the cohomology, étale cohomology, no matter what this is, of this variety. And so if you want to have analog of that, that's what Deligne provides to us. He says that the cohomology of this manifold, I mean variety of complex numbers with real coefficients, is a mixed Hodge structure over R. So this is Deligne. And this means, as I just explained, that the Hodge-Galois group acts on this vector space. But this is not how Deligne constructs this Hodge structure. He does this linear algebra and uses linear algebra definition. He never used G-Hodge. But if you go to arithmetic, the analogy is much finer. I mean, the story is much finer because the same Galois group acts everywhere. It acts, I mean, if you ask a question, how did we get acting Galois group on something like étale cohomology? And the Grothendieck says that it acts on étale side. And therefore, it acts on on categories. It acts on categories of étale sheaves. And therefore, because we can take constant sheaf, we come from here to the fact that it acts on the cohomology, because this is just the X group between the simplest étale sheaves. And because Galois groups act everywhere, it acts there as well. Now, when we go to the Hodge story, nothing like that happens so far, and there is no étale side, no étale side basically. And it was a dream of Beilinson. I can put it like Beilinson's dream, to have something like Hodge side. But he didn't quite say what it could be, but just said that it's very unfortunate that we have étale side here and nothing there. And so the proposal, which is the main idea of the story I'm talking about, is that one have at least some approximation to this Hodge side, and it's given by this Hodge quantum field theory. And generalized green functions and so on. So that's a proposal. Let's assume, let's first of all give yourself some data. Let's assume we have a map of complex algebraic varieties. Let's call this map P. So we want to do things relatively. And then the proposal is that there exists some structure. You can call it open string structure. Where on, first of all, the derived category of all holonomic D models on X, on original X. I draw here X curly. Now, again, as stated so far, it's not clear what it means, just a slogan. But in particular, it includes, as a data which we kind of can construct and observe, some correlator functions, which I call Hodge correlators. the base plays a role, but huh? No, it does play a role in the properties of this situation, but and actually, okay. Yeah. So there is a Hodge correlators between holonomic D models, between reducible holonomic D models. And let me explain actually now more carefully what this means. So first of all, you start, what does it mean to have open string theory data or something like that? So you start with a topological surface, which have holes. And in addition to holes, it has some marked points on the boundary. And it's oriented. And these marked points are considered modular isotopy. So then actually it's convenient to shrink holes which do not have marked points to punctures. So you may have puncture here, which also kind of consider red, and call special points. So I have special points. It's a puncture. I mean, then there's no point. Let's not discuss this. So special points means this red points and this one. So it's marked points and punctures. And so what we want to do, we want to assign to special points objects, actually irreducible objects of our category. Let's say it's DB hole, but could be something else. And then the geometry says us that between two consecutive objects there is orientation. So there is an arc which go in between two objects. So you can have some point S here and some point T here. And then there is an arc which go in according to orientation of the surface. And then we want to assign to this arc home of AS, the objects. Let's call this object AS. So to S, we assign this between AS and AT. And people recognize that I mean, I call this open string theory. I'm not sure how I can call this. But that's what happens a lot. And for example, was subject of paper of Greg Moore and Graham Siegel. I mean, and Maxim and Kevin Costello work in a situation which like that. So that happens quite often, such setup. And so now, what I wanted to do, I want to say that these correlators, so this, we should have some, so these correlators, they assigned to this data, to the surface, which is decorated by some objects and morphisms to all this data. So we should have Hodge correlators, which are something which lives on the base. So the point is that this, we should have Hodge correlators, which is assigned to S, and some data for your category. And this guy lives on B. S is a topological input. It's a decorated surface. So this S is decorated surface. Yeah, that's a good point. And then it's not only decorated, but it's inhabited by some objects of some category who have some social relationships, like they have homes to neighbors, which live to the right. And so to this data, we associate something on B.
And that's in the form of structure or really topological? It's topological or Riemann surface?
No, this is topological. Yeah, but the input is algebraic variety over B.
And what you do with the puncture?
Huh?
What you do with something?
So let's So I'm not going to do this full strength, of course, but I'm going to give some examples. So for example, who is our green function on a curve? So this will be the correlator which is assigned to this picture. So you have a disk, and on the disk you have delta function at x. This is little x. Delta function at y. Then you have, I mean, in our station which I considered, I just have a trivial local system, constant local system here. And then as soon as you have four objects like that, constant shift maps to delta functions in obvious way, and dually delta functions maps uniquely to constant shifts. So there is a data like that. And so you can ask, if you believe to what I said, you can ask a question, what's going to be a correlator of that? And the answer is this is a green function. It turns out to be. Now you can ask question even more generally, what will happen if I do this like delta x?
Green function is special to each structure now.
So I started with a curve here. I started with algebraic variety, which now I make a curve.
Okay, now it's okay.
Yes. Now I'm slightly cheating here, but I said that I consider delta function x and delta function y, and I explained that to talk about green function, I need to have a little bit more of data. But if I replace delta x and delta y by this delta of divisors, then the statement is completely accurate. So, and I can make sense of this. I just don't want to proceed there. But more generally, you can have now x any compact, smooth algebraic variety over C. And you can have any two irreducible local systems, let's call them L and M. They're irreducible local systems on X. And then there are trivial morphisms here, obvious morphisms this way, and there are obvious morphisms the other way. So this diagram gives you immediately some guide for which you can take the correlator. And then again, I kind of postulate that this will be the green function, but now defined depending on this pair of local systems. And I need to define what this is. So that's my next goal. So I need to define you what this guy is. And then you will see what the ambiguities and so on. So before I do that, let me be a little bit more specific about correlators of whom I want to consider in the lecture. Well, I want to define the lecture. So I want to consider the graded category, which I called, probably not me, Carlos, the category of harmonic bundles of X. And so the objects of this category are semi-simple local systems on X. And the homes are defined as, so if you take home between local systems L and M in this category, this is just the X group between these two local systems in the category of shifts on X. So it's a graded vector space. And why actually I consider this strange gadget? Because there's a very deep work 20 years ago. So Hitchin, Donaldson, and Simpson, I mean, if you combine what they were saying, then you get the following situation, the following result, that if you have L, which let's say is simple local system on X, then Hitch and Donaldson, so they prove that there exists a unique harmonic up to constant harmonic metric on L. And then Simpson, so he took this harmonic metric and he worked out the classical Hodge theory package. As Carlos was saying, there were some revolutions, and so this revolution was to realize that you can run Hodge theory on arbitrary local system, not necessarily on variation of Hodge structures or something like that. And so you can do that. And in particular, this provides the usual setup, D, D bar, and D, D bar lemma, and harmonic forms. So all this you can do on the de Rham complex of X with coefficients in irreducible local system. Now, after that, I can tell you what the green currents are in this setup. So the green functions, again, are solution of the differential equation. The dd bar of some current equals to delta function. But one needs to be just a little more careful by setting this. So green currents so given L and M as before, as on the right-hand side, on some variety x, which has dimension over complex numbers n, there exists a current, not uniquely defined, which one can call the green current, GLM, which is a current on the n-1, n-1 distributions on x cross x, with coefficients in a local system, which is basically home from L to M, tensor home from M to L. The only problem is that this local system lives on x, so you have to pull it to the square, and you have to pull this to the square. Now you get local system on the square, so you take distribution z local system, and it satisfies the famous equation that 1 over 2 pi I dd bar of this phi, of this GLM, equals the delta function of the diagonal, which may be defined because we take delta function with values in some vector bundle, but there is a natural constant shift sitting there because it's just home L to M from M to L, minus a harmonic representative of the diagonal. Now the cohomology class of this is 0. And so dd bar lemma and Carlos Simpson tells us that there is a solution. And we take the solution. It's not unique, defined up to d or d bar of something, but it exists. And this is what I want to put as something which corresponds to this diagram. And you see now that, it has these two local systems, but it's actually a correlator. It involves other 2 points, and it makes this whole thing somehow run over the base, which is x cross x. It's no longer a function of the base, it's distribution. And actually, I mean, it's generalized form it's differential form, degree n minus 1 and minus 1 with generalized coefficients, but still it lives on the base, and that's what the correlator tells you. I still want to present this in a little bit more picture way. So how we think about this green function? So again, we have L, one local system M, another local system. We have x cross x, which somehow I think about as these 2 points. And I have homes from L to M, and homes, I mean, are homes from M to L. And so this whole picture is a kind of image for this green function. And I want to emphasize that this picture is symmetric, so you can rotate it by 180 degrees. You will not notice the difference. You might arrange the things in such a way, you'll get exactly the same kernel, green function. All right, now let's run now the construction using this green function. So So as I said, we want to associate correlators to arbitrary surfaces of arbitrary genus. And so we have to start with something. So we take some surface, so something which looks like that. It has points on the boundary. And we put some local systems at these points, L1, L2, L3, and so on. This is inside of the surface. Unfortunately, this is just a disk, but it could be something more complicated. I just don't want to go into drawing of this thing. So let's just stick to the simplest picture. And then you need to take some ideal triangulation of that. So this means that you draw some diagonals inside. And so in general, you take a decorated surface S and pick an ideal triangulation, let's call T, of this decorated surface. So now I also need some other gadget that appears from nowhere as a twister plane, C2, with coordinates Z and W. This is the twister plane. the same one everybody talking about when talking about twistors. And then when I have an edge, let's say I have this edge, E, internal edge, I want to put to this edge a green function, the following conversion of this green function. So I call d c e of GE. And this is by definition the following. So you take differential one form on this twistor plane and plus some linear differential operator, ZD bar. So you apply this to the green current you have by theory of harmonic bundles. And then you also multiply it by something looks innocent, some formal element which has degree +1, which corresponds to this edge. I'm not going to explain right away, at least, what the meaning it has. But then if you count, you will see that this whole fellow has degree 2n. Because the form has degree 2n minus 1, then you have one form here, or differential operator, degree now 2n minus, the form has degree 2n minus 2, then you have degree 1 differential operator, and some other degree 1 element. Now, then what you do, you cook up the product of these guys. So you take these guys which are assigned to the edges, to all internal edges. And it doesn't matter in which product you multiply them because they're even. Then you take a trace of this. I'll explain this in a second. But you also need to multiply this by some harmonic forms which you put on the external edges. And that's important on its own. So here, so we have green forms here. And so here we have some harmonic forms. Let's call this alpha 1, 2, or just call it alpha f assigned to the wedge f. So we put some harmonic forms here, which represent some classes from here to here. And we take the product of all of them somehow. And then what we get a differential form with singularities. That's one problem. But another thing is that it takes values in some very complicated vector bundle with connection. And so we kill the vector bundle by taking traces. It's a little technical thing to do. I'll tell you in a second what this is. And then at the end of the day, you just get a differential form with generalized coefficients. Now, who these traces are, I can say it here. If you have a triangle in this triangulation, let's call T, then you have like L1, L2, and L3 sitting here. And you take home from the previous to the next one. 3 homes appear here on the sides. And there's a natural trace map to C. So this is a trace map over the triangle, and then it takes the product over the all triangles. And that's the form which you cook up on the base. So where it sits? It sits, it's a form on, what? Yes, if you ask, I'll explain in a second again the structure.
You're writing letters. It's a product of a triangle.
Yes, all triangles.
The T under triangle, is that the tau? So T is tau. T is there.
What?
Oh, that is a T.
This is T. This is T. So what I'm doing, I'm saying that I have I have this green current sitting here, harmonic form sitting here. They live in some vector bundles, but then these vector bundles, as you can you? Did I erase this? Oh, sorry. Did erase this. So, oh no, it's there. So you associate these homes to kind of oriented in two side edges here. So going like this way. And one-sided here, orient here. Then you can shrink all these triangles, apply trace on each of the triangles, you kill the coefficients. All right, so this is not yet what it's supposed to be. The last step, we need to take summation over all triangulations, equivalence classes of triangulations. And so the last step of this definition is this. So the Hodge correlator of these harmonic classes is defined as the following. So you take this form kappa t assigned to a single triangulation. You take the sum of these forms over with the weight over all triangulations, equivalence class of triangulation, of all equivalence Azimuth class of triangulations. Then you take sum over all surfaces, isomorphism class of decorated surfaces, which you can somehow put using the same data on the boundary. And then all this you integrate over where it sits. It sits on x over b raised to power given by the triangles of this particular triangulation T. And the point is that what you integrate is a current. So you can run the integral. And so in the end of the day, you get something. What is this something? So what this integral means, again, so you have, so originally you have differential form which lives on x to triangles of T. Oh, sorry, x of, yes, triangles of T. And then when you integrate it down, you get it just as x over b. You get just to the base. So you have a bunch of varieties which sit over the base, and you take the fiber product.
And products also for green functions of fiber product over base, yeah?
Yes. Yes. I'm sorry, yeah, it's a fiber product, yes. Yes. So you get something on the base. Now the question is, what this is on the base? And in principle, the construction tells you all the algebra behind, but algebra is nice, and let me work it out. So what is on the... first of all, once again, so this is a key point, so let me kind of summarize what we get. So we start with a single decorated surface, and we put some inhabitants, some object on this decorated surface. They have homes from one to the next one, and we represent these forms by harmonic forms. And then we do something with the inside of the surface, create some kind of current using green functions, integrate, get something on the B. Actually, not on the B. We get something which lives on B cross C2, twistor line. Because if you look at the definition of the green function becomes a differential 0 or 1 form along the C2 variables as well. And that's very important. So get something which lives here. Now, what are the properties of this something? So let me just say the format. First of all, I consider this construction as a multilinear function of these harmonic classes. And I can do this just by saying, it's a kind of formal remark, I can put on each edge Casimir of f, which is element in home from L1 to L2, which sits on this edge, to the dual space to this home. And so my harmonic classes sits here. And so I can take just the identity map, which sits here, integrate over these classes, and then on the output I get something which lives on the dual to the home spaces. So if I proceed with this, then I get some class. So I get a single class. This is Hodge correlator class, which looks like as it lives in some de Rham complex on B, tensor forms of degree less or equal than 1 on C2. And then it lives in some linear algebra setup, which is related to this harmonic category. And so now the question is what this guy is, where it lives. And it's very easy to see what it is, because when we're talking about this construction, so we take a surface, and so we put some objects on the surface, and then after dualization, what I put here dual to homes to each of the edges. And so I basically have tensor product, cyclic tensor product of the homology groups here, dual to homes, and then take symmetric product over all holes which I have. So this is what the construction gives you. And I denote it just by some letter. So that's kind of huge linear algebra guy which you assign to your category. So I will define in a second, but so the main claim about this is going to be the following: that this guy has a BV algebra structure, And therefore, if you take this guy shifted by -1, then this is a differential graded Lie algebra structure, Lie algebra. And so I get differential one form which lives in some DG Lie, some universal DG Lie which relates to a category. So now the main claim, which I maybe put here, tells you what is a single property which this this correlator satisfies. I will tell the definition of this a little later. I just want to give you somehow the setup. So the key property is that if you consider this guy, let me put here little zeros, so I take sum over connected surfaces. This, I mean, if you don't follow, it's fine. Just want to make the correct statement. So the main theorem is that there's a differential here because it's a BV algebra. This is not just a BV algebra. I mean, this is a variation of BV algebras because you have a base. And over this base, you have your varieties sitting. And in each of them, you have these categories. And to each of these categories, you assign some BV algebra. And altogether, the whole variation, which is a variation of pure twistor structures, or let's talk about Hodge structures, just restrict to Hodge local systems. So Hodge structures. So, but in particular, you have a connection, which I denoted by D. And so now the statement is that if you consider this D plus G0, this is just a DG connection on this B cross C2. And this is the first claim. That's already a claim because you have lots of forms here and some complicated graded object here, differential graded Lie algebra. And so altogether, it still sits in degree 1. And the second property, that if you take this connection, it's not flat, but if you restrict it to the line where Z plus W equals to 2, and this is flat. And that's the main property of this construction. So you get flat connection with values. Huh? There is a C square which appears from nowhere.
It's still on the board above you, above our head. Z and W are the coordinates.
Yeah. So you yes, thank you, Don. So you have Z and W, which was part of the definition of this kind of modified green function. So the modified green function was a function which was a form which depends on the Z and W. And the key property of the object which I get, that not that it's flat, it's not true, that it becomes flat when you restrict to this twistor line. Now, let me reformulate this again, postponing discussion of what this SC is, in a different way. So here's a different way to say this. So just from linear, it needs a little discussion related to Hodge structures. So far I just said that I produce flat connection. But now I claim that this flat connection has some Hodge meaning. And here's what it means. So first of all, given this is some kind of result. Given a complex of variations, let me assume that they're pure Hodge structures, real Hodge structures. Let's call them M on B. I can define a functor which takes this M and makes a complex out of this, CH star of B with coefficients in this variation. There's some construction, but the properties of this construction, which I'm going to use, are the following. That first of all, the meaning of this CH is this, that this CH BM is nothing, it's calculated, so it's quasi-isomorphic to R home in the category of R mixed Hodge structures from R of 0 to this M. So you can just say this is Hodge cohomology, or people called absolute Hodge cohomology of this variation. So it's a complex. Now, there's a product structure in these complexes. There's a so if you have two variations, N1 and M2, then you can take CH, I'll skip B, and CH of M2, and there's a map to CH of M1 tensor M2. And this map is commutative and associative on the nose. This is its main property. Not up to something, but on the nose. Therefore, and the last, and only 2 blackboards here. So the last property is this, that if you take any element which lives in CH1 of this fellow on B with coefficients in endomorphism of a certain variation, and you assume that it satisfies Maurer-Cartan equation, then this produces you a variation of mixed Hodge structures. On B. That's called M, which mixes the original one, which means that the associated gradient for the weight filtration of this guy is the original variation M. And so basically it says that if you start with some variation of pure guys and you want to get something mixed, all you need to do is produce some Maurer-Cartan element in this Hodge in this complex C1, which calculates absolute cohomology group. Not very surprising. The surprising thing is that there exist such complexes which are commutative associative. But then it's kind of natural. But then if you do have such a machine, then you can say that if you started with any kind of linear algebra dated, for example, you started from a variation of BV algebras, like in our case, it was S, C of category of harmonic bundles. Then you apply this machine, CH, and you produce another BV algebra. This was variation of BV algebras, but now you produce another BV algebra, just CH of har XB, and this is just a BV algebra. So this is a variation over B, and this is just an algebra over complex numbers. So now I can formulate this theorem in a different way. I can just say that this is equivalent to another theorem, theorem 2, which says that the total Hodge correlator class, which I can denote by G. First of all, this is the exponent of the one which corresponds to the connected surfaces. Secondly, it lives in CH0 of this BV of this SC of harmonic bundles. And finally, and most importantly, it satisfies the quantum master equation. So there is a total differential on the thing which I didn't actually define yet, and so it kills this element. So this is the BV differential. As I said, I didn't define yet the BV algebra structure, but if you believe me, it exists in variations, and there is this BV algebra, there is this is a BV algebra, so there's a differential there. And this is just equivalent. If for those people who know the formalism, BV formalism, you immediately recognize that this is the same as to say that if you just consider this G0 and shift it by -1, it satisfies the Maurer-Cartan equation. With respect to this product which I was talking about there. Notice this is Maurer-Cartan in a quite non-trivial BV algebra. You have to start with this linear algebra game on your category, and then you apply CH functor to this. So you get this BV algebra, and so you get Maurer-Cartan element there, or solution of quantum master equation, or flat connections. They're all the same. Now, what is good for? So how we get back to the goal which was originally formulated?
Can I just ask, when you say BV algebra, do you mean BV infinity algebra or BV?
BV algebra. differential graded algebra with a Laplace operator, BV Laplace operator, differential, etc.
So that comes from a very careful choice of Aholm, or it's the specific choice of C harmonic that allows you to do
No,
this.
So it's a choice of harmonic form or wrong?
No. I mean, this is a formal construction. You take any category, like graded category, you can run the construction. You don't need any assumptions.
Yeah, but your explicit representative depends on choice of harmonic form, yeah?
No. This is another story. So you're mixing two stories. So first of all, the definition of this BV algebra is quite universal. But the property is that you get solution of you get element which always satisfies the quantum master equation. But if you choose a different representatives, it will be not exactly this one, but the one which differs by the BV differential. So its cohomology class is uniquely defined. So let's just summarize what we have. So first of all, as I promised, we should have something when the base is just a point. And so if the base is just a point, then I claim that what we get is just a Lie algebra map. I'll explain why, but we get a Lie algebra map from Lie U Hodge to this BV algebra as BV Lie algebra connected of har x to get that Lie algebra shifted by -1. So this is just, it's just a reformulation, one more reformulation of the properties of the Hodge-Galois group and what was done. But now you can say that this is kind of quantum situation. So this is of a point, but this is like G quantum. You use all surfaces to do this. But if you decided to go only to surfaces which is on the disk, so then you get G classical. So that relates only to the disk, these points. Then you go to something much smaller, which is the cyclic homology complex of this category. Tensors of fundamental class of your manifold, shifted by 2 as far as I remember. And there is a natural projection from here to here. And so now this Hodge correlator construction, it gives you this map, it gives you this map. But now the classical one I can interpret because I can say, this is the last thing which I'm going to say, but let me still do it. There's some kind of formal arguments familiar to the people who work with this algebra, that if you take CC of the category, let's say tensor is H to N, then this maps to H0, this maps to A infinity functors. Take H0 here. From your category to itself. Again, I'm explaining this in a very loose way because I don't explain you why, I'm just saying that that's true. So this gadget, A0 of this maps to infinity functors on your category, and that's where your Lie algebra goes. So this means that it goes here to this, that you go here to this functors, A infinity functors on your category. But on the other hand, this, there is a piece of derived category of holomorphic D models, which consists of smooth D models, D smooth of X. It's D models whose complexes whose cohomology are just smooth local systems. And you can say this is just functors from, let's say, bar construction of this applied to this category to vector spaces. No matter what this means, it's just that you have your category and then you take something like DG functors from this category somewhere and you recover your category. So again, forget about details. The point is that you start with this nice category which Simpson considered harmonic bundles, and by formality it knows and recovers the whole D smooth on X. in a functorial way. It's just triangulate envelope of this. And so if you have anything which acts by infinity transformations here, and that's what our Lee Hodge doing, it acts by infinity transformations here, this just means that it acts here. And that's all. That's what was promised. So I promised that in the end of the day, when B is a point, so B is a point, we are going to, actually, did I ever say this? Sorry. Oh, I didn't. Sorry, then, sorry, I need to do this. I need to say what the output is. I thought I did. It's just 1 more minute. This tells you what you get in the end, what's the structure. So this is a summary of what we get. So what this quantum Hodge field theory tells you. So when you're on the disk, the classical Hodge field theory, which is a disk situation, that's by definition what is. This gives you the Hodge side. And what this means, how I understand this means that I get functorial homotopy action of, let's say, Liu Hodge, I'm not talking about C star cross C star, by A infinity equivalences of the big category. Now I'm talking about what it should be in general. Now, and this is what was hoped for, because I started with some manifold X, which was complex manifold. And I was saying that the dream is that there's some manifold, if this has dimension n over C, there should be something of real dimension 2n plus 1, which somehow is fibered over B over Hodge group, in particular B of U Hodge. And this means that in some sense, this group have to act here. But it doesn't. It doesn't act on this. There is no spatialized that. And it doesn't, and there's no action. So what is happening is that instead of this picture, we take this thing. So we take that this G Hodge or U Hodge subgroup acts by A infinity transformations on this dB of homomorphic X. And that's what we keep in mind when we say that there should be some kind of picture like that. That's this arithmetic side. This is like gadget for arithmetic side, and what replaces the action of the Hodge-Galois group on the category. But this is just a disk sector, and this is actually only the case when B is a point. Now you can ask what happens if B is not a point. For any B, I'm not going to elaborate with this, I don't have time, but, oh, yeah, I have to stop, just a second. So for any, I get some language to develop Hodge theory of the base. But now the last word is that now if you do the real quantum Hodge field theory, and the correlators are already, we have the correlators that satisfy master equation. So this should go to the deformation. Over the case when B is a point, let's go to deformation of this picture. Thank you.
Any questions? Yeah. Could you say something about the why there are no issues with ultraviolet singularities?
It would be better if they were. I didn't see them, so the integral seems to be convergent. It would be better if I mean, I check many times that over the disk there's absolutely nothing, and I think I checked that there is nothing in general, and I wish I have them.
But did you try this argument with blow up diagonals?
Yeah. There are arguments. I mean, via. I know. No, I'm saying that I think I proved that there are none of them, but I'm telling to Ken, it would be nice if I had them, but I don't think I have them, because the story can be run as a parallel to Chern-Simons, and somehow if it's true there, it's true here.
I mean, and I think a related question. So, like, you know, in Maxine's proof of formality theorem, there was no counterterms, but you have to work very hard to show that the master equation holds.
Yeah, so here's the fact that you have a distribution. This is where the story sits. This is that you have the current, that you integrate the current. This is a delicate statement. So that's where the convergence of the integral sits. And I was saying that if I just sit over the point, So I think I'm very confident about this. And, but on the other hand, if they are slightly divergent, story would be just nicer. That's all.
So in your point 2, the deformed situation,
Oh,
can
yeah,
you say
yeah,
a
yeah,
bit
yeah.
more about, say, what's the deformed dV whole of x, for instance?
Well, I better not, because it's first of all there is this deformation which you guys consider, and I thought I'm going to run to that, but I don't quite see this. So what I'm saying here is that I produce this total green classes, and where is this picture? I think I erased this. So there is this big BV algebra, and it projects to the small BV algebra. And when you project to the small BV algebra, the data which you have here is precisely the action of the Hodge-Gallo group. Now, when you lift it to the action of the Hodge-Gallo group on this d-smooth on categorical D models. Now, the big BV algebra is a deformation of the small one, and so it's supposed to act. And what it acts on many things, and what it acts on, you can say that this is deformation of what you had before. So this kind of argument. But I am unable to, even for the case of the curve, I am unable to get to see directly that this is a quantization of the local system. It's expected, but it's not clear. I mean, you can see it's a deformation, but I can't I don't see non-commutative deformation.